Hello everyone, welcome to High Volt Academy. I'm Muhammad and today I want to talk about an important concept in engineering FEM problems, symmetry and choosing the right space dimension for your simulations. Have you ever wondered what type of space dimension is best for your engineering or FEM problem? Let's dive into why reducing dimensions can be advantageous. By reducing the space dimension, we can significantly lower the processing power and time required for simulations. Simplifying problems to 2D or even 1D can make them more manageable without sacrificing accuracy. There are two main points to consider. First, reducing dimensions should not introduce significant errors. As engineers, we must accept and manage any minor errors introduced. And second, if the problem's variable doesn't depend on one of the dimensions, simplifying is a good choice. For example, if moving along a certain direction doesn't change the variable, reducing the dimension is feasible. Let's look at some examples which I have been drawn previously. The first example is a heat transfer through a wall. Imagine a wall made of different materials. The left side has a temperature T1 and the right side has a temperature T2. Here is a quick sketch of this wall. I have added the Cartesian coordinate also here. The temperature T only varies along the x-axis, not y, not z. So if we move along the y or z-axis, the temperature doesn't change. It only changes along the x-axis from T1 to T2. This makes it a 1D problem because y and z are not in the variable. Then we can represent a problem like this. We have a line, the left side is T1, the right side is T2, and we solve the temperature distribution along this line. Now let's consider a high voltage cable with a coaxial structure, which you can see here. Here is a cross section of the cable. We have an inner circle and an outer circle. The inner one have the voltage V1 and the outer one is normally grounded. So the electric field between these two cylinders varies only along the Z and Y direction. It does not depend on the x-axis. Therefore, if you choose any cross-section along the cable length, the electric field remains the same. So we do not have X in the electric field, and this can be represented as a 2D problem. For our next example, imagine a wire carrying current with the magnitude I, and you can see the wire here. The magnetic field around it forms concentric circles, and you can see the circles in green. Using cylindrical coordinates, which you can see in here, the magnetic field depends only on the radius. In this case, it does not depend on z or phi. If we remove phi from this variable, the H, magnetic field, is only dependent on R and Z, and therefore this can be represented as a 2D axisymmetric. Therefore we introduce this sketch into the simulation like this. Finally, if the variable depends on all three dimensions, you need a 3D model. For instance, if I add another wire here carrying the same current, the magnetic field now depends on the position of both wires in 3D space, and therefore you should solve it in a 3D domain. And what is the best simulation strategy? Start with lower dimensions. If the results are acceptable, only then move to 3D. This approach saves processing time and resources. A 3D simulation requires significant power and may take a long time to converge, so it's better to validate your results in 2D first. Always begin with simpler models. If the 2D results are satisfactory, then enhance your simulation by adding more dimensions. Okay, if you found this explanation helpful, please like the video and subscribe to the channel. See you in the next video.